Okay, good morning, everybody. The attendance code is up right now. And in a second, we'll go ahead and get started. I'm just trying to get my tablet to cooperate. So a couple reminders of things that you need to be working on. Chapter 18 is open and available for you to be working on. Your next exam is November 11th. Chapter 18 will be on there, and probably also chapter 19. So you definitely need to start working on those materials now. I was talking with some colleagues last night just about what we're observing with our students, and we talked about how having deadlines that are like on a weekly basis help you guys stay on track. And I'm getting a lot of emails saying like, I missed this assignment, I need an extension, things like that. I tend to not give those extensions because one, the assignments are open for a long time and we follow a predictable schedule that's on a calendar. And two, if you get behind in this class, you're digging a hole that you just cannot get out of. And so I don't let you guys dig that hole. That's why the deadlines are pretty frequent. Your homework is all due, like everything that's going to be open before the exam from here on out is pretty much due at the start of the exam. But those reading assignments are still due on an almost weekly basis. So make sure that you're staying up to date on those top hat due dates and that you're actually doing those assignments. The whole purpose of using this textbook and using the Top Hat platform is to have that tool that's supposed to keep you on track. Another thing that I'm seeing is there is very clearly a lot of CHEM use on your homework. I cannot emphasize enough how much you are handicapping yourself if you're using CHEM on your homework. I've stopped using Top Hat homework problems for the quizzes because everybody was getting really high scores. It was pretty obvious that CHEM was being used to do your quizzes instead of just actually opening up the quiz and doing the problems yourselves. You either had like the homeworks printed out or you had the answers written down or whatever. That's obviously not acceptable. That's not how this is meant to be done. I was using homework problems on the quizzes to give you kind of a boost, but a 100 is not really a boost. And I'm seeing, really, really high grades on the homeworks and stuff, but then just not the same on the exams. And if I see, really high grades and you guys are using, multiple tries to get those, then I know that you're working the problems out yourself. But if you have one try on every single problem and you have 100s and 95s on every problem, but then you're getting, low scores on the exams, that's a signal to me that you're not doing what you're supposed to be doing. So it's not a lot of you. I'm not telling off everybody here, but I think every single person is doing a little bit of one of the things that I just mentioned, not doing things on time, digging yourself into a hole. Some of you guys are doing that. Some of you guys are doing that and CHEM. Some of you guys are just doing CHEM. There's a whole mix of behaviors here that are really just hurting you in the end. And I know a lot of you are like, well, I'm not going to be a chemist. I don't need to know OChem. If you're going to take the MCAT or anything like that, you need to know OChem and you need to know it well, and you need to not have it memorized or expect to be able to use your notes on the MCAT. So now is your chance to learn it with help. Also, I have office hours that, nobody's coming to. So please come to those things so that I can help you. Okay, I'm going to minimize this and stop sharing. Today, what I wanted to do was talk about some of the bigger ideas in chapter 18 and 19. So I'm not going over reactions from chapters 18 and 19. As far as reactions, we are in chapter 18. but they share one common aspect, which is the use of enols and enolates. And that whole idea can be really tricky for a lot of students. So today I want to spend time just going over the conceptual stuff with enols and enolates. Okay, so first up, I want to go over some pKa values that you need to know in order to be successful. The majority of what you need to know for chapters 18 and 19 is relative pKa values. So knowing these can be really important. Okay, what is the pKa of a hydrogen on an alkane? Does anybody remember?
$50?
Yeah, it should be around 50. What about for an alkene? A proton directly on an sp2 carbon. Yeah, I see Michaela put 44. That's good. It should be somewhere around 42 to 46-ish. Like it's gonna be somewhere in there as long as there's nothing else interesting on the alkene. What about a terminal alkyne?
Is that one 25?
Yep. Okay, so these are some pKa values that are important to know. We're going to move into a different category now. So now we're going to be looking at the pKa values of hydrogens in the alpha position. So remember that relative to the carbonyl carbon, this is the alpha position, so one carbon removed. Let's review that real fast. Let's say we have a ketone. One carbon away from the carbonyl carbon is the alpha. So that can be in either direction. The alpha carbons can be identical to each other or they can be different depending on the symmetry of the molecule. In this case, these two alphas would be different. And then from there, you just follow the Greek alphabet. So alpha, beta, gamma, delta, epsilon, just keep going on forever. So when I say alpha and beta, I mean alpha is the carbon directly attached to the carbonyl carbon, and beta would be two removed. So does anybody know the pKa of a carbon alpha to a carbonyl, a ketone or an aldehyde? Okay. This is going to be about 19 to 20. And oftentimes we'll call this the alpha proton because ultimately it's going to get deprotonated. And so we tend to talk about it as a proton instead of as a hydrogen atom. Also, something I want to point out is when we're talking about an aldehyde, the pKa of this hydrogen is still going to be about 19 to 20. What we don't want to do is think about this proton. We are never going to remove the aldehydic proton. That's just not a thing that we do. So don't deprotonate the aldehydic proton. The next one, if we have a dicarbonyl compound, the proton that's on the alpha carbon in between the two carbonyls, do you think this is going to be more acidic or less acidic than our first type of proton here? Is the proximity of polar electron withdrawing groups going to make it more or less acidic? Yeah, I see several votes for more, and that's true. So this is going to be more acidic. That's going to give us a pK of 9 to 11. Oh, I accidentally skipped one. Oops. The ester also. Whoops. If we have a hydrogen alpha to an ester, this is actually going to be a little less acidic. We'll talk about why in a little bit. So it's going to be about 25. So if we have a proton on a diester, it's going to be more acidic than the proton that's alpha to just a single ester, but less acidic than this guy. The pK of this one specifically, because this is a specific compound, is 12.9. And this is diethyl malonate. I'm giving you a name because you're going to see this compound approximately 10,000 times in the rest of the semester. That's a gross exaggeration, but also not as much of an exaggeration as you would think. Okay, does this make sense so far? Okay, so let's talk about where this acidity actually comes from. Okay, so we're just going to draw some generic ketone here. We have 2-butanone. If we want to pull off this proton off of 2-butanone, we can pull off this hydrogen, put the electrons on the carbon that we're pulling it from. This is going to give us a carbanion. Now, is a carbanion something that we make often? Do we see this a lot? No, we don't see this a lot. So that probably tells you that this is a fairly reactive species. It's not overly stable. At least a regular carbanion is not. This one has something special going for it, though. Does anybody know?
It's got a resonance.
Yes, awesome. This is going to be resonance stabilized. So we can take these electrons and push them up onto the oxygen. So having this resonance form stabilizes this. And if your conjugate base is resonance stabilized, that means that the acid is going to be more acidic. Another thing that somebody mentioned in the chat is the electron withdrawing groups, right? That's going to be a big contributing factor, and also a big contributing factor to why having 2 carbonyl groups makes it more acidic. So the really big thing that I wanted to talk about was those resonance forms. Those are a key reason that this is possible to make, that proton is more acidic than you would expect it to be. But another reason is because the ketone is pulling electron density towards it. So remember, this is also an alpha proton. Both of these can be deprotonated, and we'll talk in a little bit about how you know which one is going to be deprotonated, because it does actually matter. But because the oxygen is pulling the electron density towards it, that's going to make this more acidic because we're pulling electron density away from this carbon, which weakens the bond between the carbon and the hydrogen. Now, this is like basic stuff from like what, chapter 2, 3, when we talked about acidity in OCHEM 1. So if we have 2 carbonyls, we have double the dipole. So the pK of this proton is going to be around 9 to 11. What about the proton that's on the other side of the carbonyls? What's the pK of this one?
19 to 20.
Yeah, it's going to be around 19 to 20 because it's only really being affected by this one carbonyl. And then Justin asked a question. Yes, the reason I drew this one was because these are both alpha protons. Just like in this case, these are both alpha protons. So we're not going to discuss which of these is going to get pulled off just yet. We're going to do that in a little bit. But as far as this compound, let's call this HA and HB. Between HA and HB, if I threw a base into a flask that contained this compound, which one would be deprotonated, HA or HB, or both?
B.
Which one is the most acidic?
A.
Yeah. So HA is more acidic by a lot, right? To us, that looks like, just 10 points, right? Like 10 points on the pK scale. But remember that for every point on the pK scale, this is actually an exponential scale. So the difference between HA and HB is about 10, which means that the proton HA is 10 to the 10th times more likely to be deprotonated than HB. So if you were to throw in a base, 10 to the 10th times HA would be deprotonated for every 1 time that HB would be deprotonated. So the chances of HB being deprotonated is pretty negligible. Does that make sense? Okay. I also wanted to talk about why the esters are not as acidic. So the esters are kind of confusing because you look at the ester and you say, well, there's twice as many oxygens there. So the dipole is twice as strong. And therefore, the hydrogen should be more acidic, right? That's one source of logic. But the issue here is actually the resonance forms that are formed when you deprotonate it. So if we deprotonate the ester, we have the resonance form that we looked at earlier. So that's one. But another thing that can happen is we could create a double bond between the oxygen of the ester. Which is kind of a disaster when you look at the deprotonated form. If you were to do this with just a regular ester, you can see just the charge separation. Is this a good resonance form? Is this likely to be a major contributing resonance form?
No.
No, it is definitely not. But what it does tell us is that that oxygen is electron donating in the direction of the carbonyl carbon. Because just because it's not a major contributing form doesn't mean that it's not there, right? The fact that we can draw it means that it is a contributing form in some way. And so since some electron density is being pushed into the carbonyl from the, I don't know why I'm drawing it on that structure. Let me draw a new structure. So we have electrons being pulled from our alpha carbon by the carbonyl, but we also have electrons being donated by our alkoxy group. And that's why the proton on the ester is not going to be as acidic as a proton on an aldehyde or a ketone. It's because it has that one crappy, not huge contributing resonance form. Okay, does this make sense so far? I promise I'm getting somewhere with this. So when we deprotonate our carbonyl compounds and we draw out our conjugate base, we have this form and we have this other resonance form. Which one of these is the stronger resonance form? The one that least offends all of our rules?
B.
Yeah, B is definitely the one that's the least offensive to us. Why is it the least offensive? It has the same number of covalent bonds. In both of these structures, everything has a full octet. Why is this the least offensive one?
Carbon doesn't like to be negative.
Yeah, because we put the negative charge on the more electronegative atom. So naturally, that's going to make us like resonance form B a lot more. But which atom do you think the negative charge is actually focused on? Which atom is the nucleophilic atom here?
Carbon.
Yeah, it's actually carbon. So even though we often draw, this is called the enolate. I meant to introduce this and call it the enolate so that you knew the term. We tend to draw the enolate in form B, but its reactivity actually is like form A. So the whole purpose of this is that enolates are nucleophiles. And so are enols. We saw an enol briefly last chapter when we discussed decarboxylation. So enol is just an enolate with a proton on the oxygen. Yeah, so the purpose of both of these is that they are nucleophiles. So when this reacts as a nucleophile, it is the carbon atom that is nucleophilic. Same thing here. Also, you're never going to draw the enol like this. Do not do this. There is a neutral option. Draw the neutral option, please. Even though that is a valid resonance form, we're not going to draw that. So the carbon is nucleophilic. Okay, so the next thing that I want to talk about here is how much of the enolate is formed and our dependence on the identity of the base. So there are two main reasons that knowing your pKs and knowing the differences between bases matter. One, the strength of the base is going to indicate how much enolate is present. I'm not gonna write emo. So how much of the carbonyl compound was deprotonated to make the enolate. The other thing is the base indicates partially which alpha proton is deprotonated. So there's a couple factors there, but one of them is the strength of the base. Okay, so we're gonna address number 1 first. So we're gonna start with acetone, and we're gonna react it with 2 different bases. Okay, I'm gonna put you in your breakout rooms for about 2 minutes of deliberation. I'm gonna give you a minute and then I'm gonna close the breakout rooms, and there will be that one last minute where you do not have to leave your breakout room. You can stay in there, but you're gonna have 2 total minutes to work this out. What I want you to work out is which one of these which side of the equilibrium is going to be favored. So you're gonna have to draw the products for both reactions and then determine which side is favored. Is it the products or the reactants? So those are your 2 tasks. 1, draw the products. 2, determine the direction of equilibrium. Are we favoring the products or the reactants? Okay, last class we talked about how maybe having larger breakout rooms would be helpful. I'm gonna put you guys into 5 breakout rooms, that's 13 participants. And I want all of you guys talking to each other. Oh, and where are you? Let me do a co-host first. There you are. Oh, can't do that on this one. Gotta do it over here. Okay.
You're muted.
You're muted.
Oh, sorry about that. Did we feel like we got the products and we figured out the direction of the reaction?
Nothing on direction.
Okay. So in both of these reactions, we're going to see the deprotonation of the alpha proton, right? So we're looking at ethoxide pulling off this proton, and then you can draw whatever form you want. Let's go ahead and draw one where the negative charge is on the oxygen. So we're just going to draw an equilibrium arrow for now. We have our enolates, and then what is our other product?
Ethyl alcohol,
Right.
but also there'd be the other resonance form of that, wouldn't there?
Right, but they're not different molecules, so we only need to draw one.
Okay.
So how do we determine the direction of this reaction? What information do we need?
pKa.
Right, we need the pK values. What do we need the pK values of?
The alpha protons?
Yeah, so we need to know the pK was alpha proton. What should it be? What range?
That one's the
It-
19 to 20.
Right. So somewhere around 19 to 20. What is the pKa of ethanol? Yeah, Michaela got it in the chat. It's around 16, right? So which side is going to be favored? What's our basic rule here for any acid-base equilibrium? Which side is favored?
The lower one usually, right?
What do you mean by lower?
Lower pKa?
The
Well,
less
so-
acidic or
yeah,
more acidic.
no, we're looking for the opposite, right? If we create something with a lower pK, that means it's more acidic, it's a stronger acid. We want the weaker acid. So which side of this reaction is going to be favored, the products or the reactants?
Reactants.
The reactants, right? So the reactants is going to be favored. Looking at the difference between the two pK values, so we're talking about, let's just pick one, 19 versus 16. Are these very different?
A little.
Not really.
They're not that different. They're only about 3 pK units. So we're looking at a difference of 10 to the third versus 1. That's not that different. That's not too crazy. So we are going to favor the reactant side, but it's not like a very strong preference. Let's look at our next reaction. We're going to do the same thing, right? So this is a base. It doesn't matter really if you know what the base is, you know what this reaction is going to do, right? We're making the enolate. And what is our product? What functional group are we making?
An amine.
Right. So all we're doing is putting this hydrogen on here. And we'll still have a lone pair. There are actually 2 lone pairs here. Okay, so this compound here, we're going to go over in detail later. It's called LDA, which stands for lithium diisopropyl amide. So it's a deprotonated amine. What's the pK of our amine? We don't have to know the exact pK for lithium diisopropylamine. We know a rough number for all amines, or we're supposed to. Yeah, so Justin got it in the chat. He said about 36, and actually the pK for lithium diisopropylamine is 36 on the dot. The approximate number that I usually teach for amines is 35. Okay, so which side of the equilibrium is going to be favored this time? We have the same pK over here, 19 to 20 versus 36. Which side do we favor?
Product.
Right, we're going to favor the product. Is this going to be like a significant difference? We're talking 19 versus,
Yeah.
Yes, it is.
yeah, this one is much more significant. So we're talking 10 to the 17th versus 1 on this side. Yeah, so very, very big difference. In the top one, I would say that they're more at equilibrium, and there's kind of a slight favoring to the reactant side. On the bottom, this is really not an equilibrium at all. This is going to create only the enolate. When you put these two things together, you're going to get enolate and lithium diisopropylamine. There's not going to be any carbonyl compound left. In our top situation, you would get a small amount of the enolate, a small amount of ethanol, but mostly the carbonyl would exist. And this is really important, I promise. I'm not just picking on acid-base equilibrium because it's my favorite chemistry. It's not. But this is really, really important for you to know. Okay, so this covers topic number 1 there. The strength of base is going to indicate how much enolate is present. The next thing that we have to talk about is what if I have an asymmetric ketone? I don't know why I drew so many carbons. I don't need that many carbons to prove my point here. Okay, so we're gonna have a blue proton and a pink proton. These are both alpha protons. And if we introduce a base, we can do 2 different things. We can pull off the pink proton, and if we do that, we'll end up with this enolate. If we pull off the blue proton, we would end up with this enolate. Looking at these structures, is there one that looks like it might be the preferred structure? I see 1 vote for blue in the chat.
Yeah, the blue.
Blue.
Okay, yeah, so lots of votes for blue. Why?
It's more substituted.
Exactly. So this is the more substituted alkene here. So this is going to be the preferred enolate.
Does that make it more stable?
Yes, it makes it more stable. So this is what's called the thermodynamic enolate. This is more stable. And it's going to form at equilibrium conditions. Okay, the top one is our kinetic enolate. This one is going to form quickly because it's least sterically hindered. Okay, so now let's talk about which one forms when. So the thermodynamic one forms at equilibrium conditions. So looking at our 2 bases above, in which scenario is the thermodynamic one more likely to form? We'll give them labels. Let's call this scenario A and scenario B.
A.
A.
Yeah, A is an equilibrium scenario. We are more likely to form the thermodynamic. Enolate. So then in B, where we have a really, really strong base, is going to pull off a proton and it's going to pull it off fast, there's a higher probability of potentially forming the kinetic. So you usually see this more when the differences in steric hindrance are greater. Looking at this one right now, like you have a methyl group versus a methylene group, a CH2 group, those are not drastically different, but still, if you reacted this with LDA, you're more likely to get more of the top one. And with something like ethoxide, you're more likely to get the bottom one. The example that I put in the notes so we have a cyclohexanone here, 2-methyl cyclohexanone. If we react with LDA, are we going to pull off HA or HB? So our strong base, HB, yeah. The other great thing about LDA for choosing the kinetic enolates is that LDA is quite bulky, right? This is a bulky base situation, a lot like what we might recall with, using tert butoxide versus methoxide for an elimination reaction. So the size of LDA tells us that we're more likely to pull off HB. And if we were to react with ethanol or ethoxide, we're going to pull off HA. Okay.
Can you explain why that is again?
Because it's more sterically hindered. It's going to give us the more substituted alkene, and therefore it's the more stable alkene. And when we're at equilibrium, we're able to choose the more stable outcome. Because imagine that, the ethoxide does pull off HB. It's eventually going to equilibrate to where we have the alkene that was only made with HA. So remember, like if you're in equilibrium, you're picking up the proton, you're getting it pulled off, and then it comes back on. It's proton on, proton off, proton on, proton off, until the only enolate that you've made is this one. So just going back and forth. So anyway, the reason that I wanted to do this, even though we didn't do any reactions today, right, other than acid-base reactions, is for chapter 18 and 19, the big thing that you need to know at the start of any problem is which enolate is going to form. And then when we get to chapter 19, especially how much of the enolate is going to form. Those are the two really, really important questions at the start of any reaction at the alpha carbon. And that was the entire point of today. Are there any questions? Isaiah, that's not a stupid question. This is chapter 18. So this was all from the start of chapter 18, and it's going to be applicable for the next 2 chapters. All right, well, you guys are free to go, and I will upload this video when it finishes downloading to my computer.
Quick question.
Sure.
Is chapter 18 going to be on Top Hat or?
Yes. Is it not on Top Hat yet?
Not on my end.
It's not.
Unless I just need to refresh. I don't.
No, it might not be on Top Hat, but the entire module is up. I posted all the notes and stuff. So that's all there.
Okay, cool. Thanks.
Oh yeah, it is open, or, oh, sorry, it exists on Top Hat, but I didn't open it. Okay, I'll go ahead and assign it now.
And so for this next test, you said 18 and 19 are going to be on it.
Yes.
Okay.
Okay, so the reading assignment is open now. And then the homework, I don't see it. I thought I put it in here. I'll put the homework in here and open that as well.
So the exam is 16, 17, 18, and 19?
Mm-hmm. Yeah, we might not have all of 19 on there, but definitely some introduction to 19.
Okay.
Thank you. Have a good day.
You too. See you guys later.